Hey friends, so today begins Unit 2 on exponents and radicals, and what we want to cover with this first lesson is we want to take a look. We want to take a look at estimating roots and understanding the difference between a rational number and an irrational number. Now, some of the vocabulary that we're going to deal with today, we have kind of dealt with just as an introductory, in an introductory way in the first unit, and we're going to revisit some of that vocabulary again because we did do a lesson in the first unit on perfect squares and perfect cubes and their roots. So if some of what I brush over now, you're like, I don't remember that, go back to the polynomials unit and look up that lesson on perfect squares and perfect cubes, okay? Okay, so some quick review of vocabulary. This whole thing here is called a radical. The n itself is referred to as the root index, okay? And then the x, the thing that's underneath the radical sign, that is a radicand ending in a d, okay? So we introduced that to you before, but we're going to use this a little bit more today, so I wanted to just review it with you. Okay, now we talked in that first lesson about getting square roots and where the square root button was on your calculator. And we talked about cube roots and where the cube root button was on your calculator. Now we want to look at higher roots. So maybe it's a fourth root or a fifth root or a sixth root. To do that, your graphing calculators are capable of doing that. And I just want to quickly review how to. So together we're going to figure out the fourth root of 52. If you are a Casio, you're going to press 4. Now, the reason I said 4 here is because I'm looking for the fourth root. Essentially, you're going to press whatever root you want, and then go shift your exponent button, and then type in the 52. If you are a TI, you're going to also start by putting in the root index into your calculator, so that's why that 4 is there, and then you press math, option 5, and then press 52. I'd like you all to do that and make sure you're getting a number that's around 2.69. I've rounded that to 2 decimal places there, okay? All right, so classifying some numbers. You have seen lots of different types of numbers before. If I asked you to just throw ideas out at me, you would say things like, oh, an odd number, or an even number, or a prime number, or a natural number, or a rational number. What we want to do is we want to look at number families for a second, see how some of these number families are connected to each other. For the most part, the definitions I'm about to give you, you should have had in grade 9. But maybe not the mathematical portion of the definition. So make sure you take note of the mathematical portion. We often group similar numbers together, or that's called classifying them. One number could belong to more than one group, just like you could be a member of both the football team and the band, okay? So just because you're on the football team doesn't mean you can't be in another group. So you could belong into more than one group at the same time. Okay, natural numbers are what we would call the counting numbers. Now, if I asked you to count something, where would you start? You start at 1 and you go 1, 2, 3, 4. Okay, so mathematically, we would say n for natural, n equals, now these are called set notation brackets. Brackets are super important in math. It matters what bracket you use, okay? Squiggly brackets versus curved brackets versus square brackets all mean something different. It's all a different context in math. So you want to be careful with that. When we're talking about groups of numbers or groups of elements, we use these squiggly brackets, which are called set notation brackets, okay? And inside the set notation brackets, we define the pattern of what the numbers will do. So we start at 1. Remember, you can't count nothing. That's why 0 is not included in the natural numbers, okay? Either you have something to count or you don't have something to count, okay? So we start at 1, then we go to 2, then we go to 3. We've established the pattern, and so then we end with that ... to say, hey, that pattern's going to go on forever and ever and ever. The next guy is our whole number family. The whole numbers are all of the natural family plus the number 0, okay? So I'm going to write W for whole, and we open up a squiggly bracket, and we say we start at 0, then we go to 1, then we go to 2, then we go to 3. That establishes the pattern that we're doing. So then after that, we will go ... to say we're going to go on for infinity. Okay, the next guy is your integer family. Now, your integer family is all of the whole numbers, okay, plus putting a negative sign in front of every whole number, okay? So we say all of the whole numbers plus their negative counterpart. So now I can be 2, but I could also be -2. I could be 7, but I could also be -7, okay? One of the biggest mistakes I see grade 10s make is I will ask them for an example of an integer and they will tell me 2.7, okay? 2.7 is not an integer. I can't be in between 2 and 3 and be an integer, okay? That's a different family and we'll talk about that in a minute. Integers cannot have decimals or cannot have pieces of a number with them, okay? So it can't be any decimals or fractions here. It can only be whole numbers plus all the negative versions of those whole numbers. So I could be -18 billion, that's an integer, but -3.2, that is not an integer, okay? Now, for the mathematical definition, I in the first two, the natural and the whole family, I had a starting number. The problem with the integers is I don't have a starting number. If you think about it, I'm going to keep going down that number line to negative infinity. So how I handle that is I actually start with a ... Okay, so I'm going to open up my squiggly bracket. I'll start with a ... and then I'm going to just show from -2 to 2. So -2, comma, -1, comma, 0, comma, 1, comma, 2. And then finish with a ... because I'm going on forever in both directions. Okay, I'm using I here for integer. It is also very, very common to see a Z for integer, just in case you see that, okay? I tend to use I. Z is actually probably, many would consider Z to be the more mathematically correct thing to use. You'll see me use I for the most part, only because that's what your diploma will usually use. So I've just stuck with that. Okay. Next up would be the rational family. Now, the rational family means any number that can be written as a fraction, okay? Now, there is a mathematical definition for that, and it looks like this, okay? Now, I want you to write that down exactly as you see it, and we're gonna just unpack what it means, okay? So this means any number that can be written as a fraction, essentially, okay? Any number that can be written in the form A over B. Now, this guy means where or such that. Okay, so we'd say any number that can be written in the form A over B, where A and B, okay, you see how we're reading this? Now, this funny looking pitchfork guy is belongs to or is a member of, okay? Belongs to or is a member of I. Well, what's I? The integer family. So we're saying A and B have to be integers. That means I can't write a fraction and say it's like 2.5 over 3. That doesn't go. That's not considered a proper fraction, okay? So A and B have to be integers, and B can't be 0. I can't have 0 on the bottom of a fraction. Division of 0 is undefined, okay? It is totally okay to have 0 on the top, okay? If I had 0 divided by 5, you are asking to take nothing and put it into 5 equal parts. That's fine. I can have 5 equal parts of nothing, and that will give me nothing. That's totally okay. But when I reverse that, when I divide by 0, if I went 5 over 0, I'm saying take 5, take something, and divide it into equal parts of nothing. That's impossible. No matter how many parts of nothing I have, I'm never going to find something, okay? So division of 0 is not possible. Mathematically, we say it's undefined, okay? It's undefined. Q is what we use for the rational family. I believe because of the word quotient and the word quotient referring to a division statement, okay? Okay. Oh, actually, I don't know if I said this. I said it, but I don't know if I showed you that. That equal sign with a slash means cannot equal or does not equal. Okay. All right, I'll clear that. And then the next family that, oh, No, I want to keep talking about this. So many exciting things to say about rational families. So these are, if I can write something as a fraction, it's one or two types of decimals. Either it's a terminating decimal, terminating just means it ends, or it's a repeating decimal, okay? So probably in previous courses, you've seen numbers like this, 2.13 with that bar on top. That means it's gonna go 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, and it just keeps going like that forever and ever and ever, okay? Repeating decimals can be written as a fraction. So either I stop or I repeat and can be written as a fraction, okay? Okay, the next family is irrational. Now, essentially, irrational is anything that's not rational, okay? So these would be two things I'm gonna say here, and you need to be comfortable repeating these two things back to me. Non-terminating, non-repeating, okay? Non-terminating, non-repeating. Non-terminating means it doesn't end. Non-repeating means there's no pattern there. There's no repeating pattern here, okay? This is a non-terminating decimal. It's gonna go 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3 forever, but it repeats, and so it's rational. This goes on forever as well because I have that dot, dot, dot there, but there's no repeating pattern in the digits, okay? So this would be considered an irrational number. It is a non-terminating, non-repeating decimal. Okay, and then this is the one word that I don't know if you would have seen in grade 9. It just kind of depends on your grade 9 math teacher. It wasn't part of the grade 9 curriculum. The real family is the union of the rational and the irrational. Now, for our purposes and for all of senior high, that's everything, okay? We don't deal with non-real numbers in senior high, but there exists non-real numbers, okay, that we do mathematical operations with, but that's for another conversation in university. So for our intent purposes, everything we see, everything we deal with in math, in senior high, will be real. Okay, so we're gonna create this little Venn diagram to show how all of these things connect to each other. So the smallest family I talked about today is the natural family, okay? Now, I say smallest, but that's a huge family, right? That's an infinitely large family because I can go 1, 2, 3, 4, 5, 6, 7 for as long as I want, okay? Then we had, sorry, the whole number family. Now, notice how I did this. The natural family is completely inside the whole number family, okay? Every natural number is also whole, but the fact that there's space out here that's not inside the natural is insinuating that there are numbers that exist that would be in the whole family but are not included in the natural family. And you know, if you've been paying attention for the last 30 seconds, that is 0, okay? That's the only number that goes in here. Then we have the integers. All the whole family are integers, which means all the natural families are integers because they're all inside that bigger pile. It's kind of like, you know, I'm a teacher at Centennial, so I'll use Centennial as an example. It's kind of like, this is everybody in Mr. Hill's class. Well, everybody in Mr. Hill's class is a member of Centennial High School, okay? But not every member of Centennial High School is inside Mr. Hill's class. Well, every member of Centennial High School lives in Calgary. So this big one could be Calgary, but not everybody that lives in Calgary goes to Centennial High School, okay? So that's kind of how this all works. After the integers, we have the rationals. Okay, so all integers are rationals, but not all rationals are integers. It's this purple space out here where you would get those decimals. Remember I said earlier that you can't have a decimal and call it an integer. It is a rational though. So 2.3, perfect spot for 2.3 right here, okay? Negative 7.9, perfect spot right in here, not in the integer family though. And then we have the irrationals, which are just beside the rationals. They are not connected to each other. There are no overlapping regions there. And then the whole thing is real, okay? whole thing is real. Now, let's try and put this into practice a little bit. First of all, what's an easy way to tell if something's rational or irrational? Well, we said that the definition of a rational is that I can write it in fractional form. So see if you can write it in fractional form. So for instance, let's just pick on 7/9 for a second. If you took a calculator, well, you know it can be written in fractional form because I just said 7/9, right? I just gave it to you as a fraction. But if you took your calculator and went 7 divided by 9, you're looking at 0.777777. Actually, this is a good conversation to have. You're looking at 0.7777777778. That 8 does not exist. Okay, so important that you understand this conversation because I don't want you to see that 8 and say, oh, no, it's not repeating. It certainly is repeating. You have to remember that your calculator is finite. Your calculator can't handle something that goes on forever. Okay, so your calculator takes the repeating decimal as far as it can go, and then when it has to stop, it follows rounding rules. So it's in its head looking at the next number, saying the next number is higher than 5, and so it's stopping the number by taking the last 7 it was able to write and rounding it up to 8. That 8 is not actually there. That's 0.77777 repeat, okay? So if you see that repeating decimal, you know it's rational. If you are unsure, your graphing calculators can put things into fraction for you. So for Casio, you just press your F to D button, or if you have a newer model Casio, that's the S to D button. And then for the TI, you would press Math, Enter, Enter. Okay, so for instance, humor me for a sec, grab your calculator and go 7 divided by 9. And you're looking at that 0.77777. Now, press your S to D button if you're a Casio, or press your Math, Enter, Enter, and you'll notice it puts it back into 7/9. Okay, now I want you to put in root 2. Okay, root 2, so you should be looking at 1.414213562. If you are a newer Casio, you might have to press your S to D button to see that decimal, okay? So when you go to put this in a fraction, the Casio kids, you're either nothing's gonna happen, or it's going, if you have a newer model, it's going to convert it to a radical for you. Radicals are not rational, okay? For the TI kids, you guys are, it's just gonna keep spitting back the decimal to you, so that tells you you can't write it in fractional form. Okay, if you don't have a graphing calculator yet, not a huge deal. You can just look at the decimal itself. You should be able to look at 1.414213562. Remember, I'm still picking on root 2 right now. You should be able to look at that string of decimals and say, okay, that is a non-terminating, non-repeating decimal, therefore it's irrational. Okay, so examples of things that are irrational: pi is irrational, 3.14, blah, 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 blah. Most roots that don't simplify to a natural number are irrational, okay? All right, so for each of the following, determine all the number families that are represented. So first guy is -3. So what's the smallest family I can fit -3 into? Well, it's not natural. I can't count -3. It's not whole, but it is an integer, okay? So it would be an integer. As soon as it's an integer, it's also rational because all the integers are inside rational, and it's also real. So you would need to say 3 things there. It's an integer, it's rational, and it's real, okay? Next guy, root 35. Put root 35 in your calculator, and you're gonna get 5.916079783. That is a non-terminating, non-repeating decimal. Okay, there's enough decimal places there that you know this is going to go on forever. There's no pattern to the numbers, repeating patterns to the numbers. So it's irrational, and then if it's irrational, it's also real. Irrational is denoted with a bar on top of the Q. In math, putting a bar on top of a letter like that essentially means it's the complement, which is it's everything that's not So Q bar essentially means everything that's not Q. So it means everything that's not rational. Okay, 2/3, that's a beautiful fraction. Fractions are not integers, so the smallest family that we can do there is rational. So it'd be rational and real. Root 81. Now, don't get caught in that statement I said earlier that said roots. You may have heard me say roots are irrational. I said roots that don't simplify to a natural number. So if you look at root 81, what is the root of 81? The root of 81 is just 9. So actually, that's a natural number. 9 is something I can count. So I can go natural, whole, integer, rational, and real. And I would need to state all of them. Natural, whole, integer, rational, and real. Okay? All right. Classify the numbers below as rational or irrational and explain. The root of 625 is 25, so it would be rational. Okay? If you're unsure of that, you just plug it in your calculator and see what you get. The cubed root of 26, I know that the cubed root of 26 is not a natural number, which means it would have to be irrational. But if you're not sure, you can stick it in your calculator, which I was doing while I was talking to you. And I got 2.962496068. That is a non-terminating, non-repeating decimal. That would have to be irrational, so that's a Q bar. The root of 9/100. Well, actually, I know the root of 9. That's 3, and the root of 100 is 10. So that is actually just a convoluted way of saying 3/10, which is a fraction, so that would be rational. The root of 0.25. The root of 0.25 is a half. You want to think about that for a sec? I thought you might. So let's do it. 0.25 is 1/4, isn't it? So if I wanted to take the root of 1/4, that would be the root of 1 divided by the root of 1/4. The root of 1 is 1. The root of 1/4 is 2. Okay, sorry, the root of 4 is 2. So the root of 0.25 is 1/2, which is rational. Root 12, sorry, fourth root of 12. I had something in the way of the slide. The fourth root of 12. Well, you can practice using that button if you like to figure out the fourth root of 12. And you're looking at 1.861209718. That is a non-terminating, non-repeating decimal. So it would be irrational. 0.8 squared is 0.64. That terminates, so that's rational. The fifth root of -32 happens to be -2. So that would be rational. The root of 0.24, 0.24 does not have a root that would be a fraction. It is 0.4898979486 for those who want to check if you did it in your calculator right. That would be irrational. Root 2 is also a non-repeating, non-terminating decimal, so it would be irrational. And then 7.23, that terminates, so it's rational. Okay? Awesome job, guys. All right, number these from least to greatest. All you got to do is stick them in your calculator so you get a decimal approximation of them, and then decide who's smallest and who's largest. Remember, the least will go to the left, greatest will go to the right. Root 17 is around 4.1. The cubed root of -8 is around -2. And the cubed root of 6 is around 1.8. So smallest to largest would be the cubed root of -8, then the cubed root of 6, then 17. All right, so now we're going to have a quick conversation around estimating roots. A perfect square, we talked about this in our squares and cubes lesson of polynomials. That was lesson number 2. A perfect square is any number that can be written with an exponent of 2. 5 squared is 25. Therefore, 25 is the perfect square, okay? So 25 is a perfect square because it can be written with 5 squared. It can be written as a number with an exponent 2, okay? it is any number that can be expressed as a product of two equal factors. So 25 can be expressed as 5 times 5. Therefore, 25 is a perfect square. A perfect cube is any number that can be written with an exponent of 3. So 3 cubed is 27, so 27 is the perfect cube because I can write it as 3 cubed. It is any number that can be expressed as a product of 3 equal factors. 3 times 3 times 3 would give me 27. Therefore, 27 is the perfect cube. Now, what I would like you to do is fill in this table before we can talk about estimating roots. So the original number being n, I'm going to go 1 to 10. I would like you to tell me what the perfect squares are that match the original number. So that would be like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, all the way up to 10. Then your perfect cubes all the way up to 6, and then your perfect fourths all the way up to 4, please, 4 to the 4. So pause me, fill in this table, and then come back and check your answers. Okay, so your perfect squares should have been those guys: 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I'm hoping you guys did that without a calculator. Remember a few days ago when we were doing polynomials, I said I wanted your perfect squares memorized up to 15. So that shouldn't have been too much of a stretch. The perfect cube shouldn't have been too much of a stretch: 1, 8, 27, 64, 125, and 216. The perfect fourths you may have had to use your calculator for, and that's okay. 1, 16, 81, and 256. Okay, all right. So thinking through all that table that you just created, how might we estimate the root of 20? So here's what I want you to think about. I want you to find guideposts for yourself, okay? That's why I got you to write all that stuff down on the table. As soon as I say I want you to estimate root 20, I want you to think of 16 and 25. Now, why 16 and 25? 16 and 25 are my perfect squares where 20 is in between. So I know that the root of 16 is 4. I know that the root of 25 is 5, which means that the root of 20 has to be 4 point something. Okay, do you see what I'm doing there? The root of 20 has to be 4 point something. Now, 20 is 4 away from 16, and it's 5 away from 25. So it's really close to the halfway point. So it's going to be really, really close to 4.5. Do you follow what I'm saying? Okay, so it's not exactly halfway though. So I would say not to estimate 4.5. I would say, hey, why don't we estimate maybe 4.4? Okay. Now, this is what I want as an explanation, okay? I don't care that you can type this in your calculator, right? That's not the point. If I ask you how you would estimate the 4.5, these are the sorts of things I want you to say. We know that 20 is in between 16 and 25, so root 20 will be in between 4 and 5. 20 is closer to 16, so our number should be lower than 4.5. It's actually not that much lower than 4.5. We're going to estimate 4.4, and then we're going to check. When I go to check, it's actually 4.472. So that would actually round to 4.5. So I would accept 4.5 as an estimate as well. But really, it's not the final answer that I'm concerned about here as much as it's this written explanation explaining to me how you would go about estimating it. Okay. All right. So now, same sort of game. Sorry, I didn't want you to see that yet. Same sort of game, but we want to do the cube root of 20. So if I'm looking for the cube root of 20, I'm still looking for these guideposts, but now I'm looking for a perfect cube. So I'm looking at a different section of your table there. You're looking for the perfect cube section. So you're thinking, okay, I've got 8 and I've got 27. I know that the cube root of 8 is 2, and the cube root of 27 is 3. So I know my answer has to be 2 point something. Okay, 20, cube root of 20. Well, I would be what? 12 away from 8, and I would be 7 away from 27. which means I'm closer to 3 than I am to 2. So I should be above the halfway point, maybe 2.6, 2.7. That would be a decent estimation of that. Okay, so I did 2.7 as my estimation. If we were going to check, we just type that in our calculator, and it actually ends up being 2.71. Okay, now a small little warning I want to give you. If I said, hey, estimate cubed root of 20, and you told me it was, my estimation is 2.714417617. Okay, again, I don't care about your calculator. You can't estimate to that specificity. Okay, so what I want from you is kind of the wording of what these paragraphs are. Okay, that's the sort of thing I'm looking for. You can use your calculator to check for sure, but your estimation, I'm just looking for one decimal place, and I'm looking for a reason why you chose that decimal place. Okay, I'm not looking for you to just use your calculator. Okay, awesome. So estimate the following roots to one decimal place. So you try each of these. Okay, so root 55, that's going to be close to root 49, which is 7. So I'd say 7.4-ish, a little past 49. Root 16 over 45. Well, you know the root of 16 is 4. 45 is super close to 49, so I would say a good estimate of that would be 4 over 7. 0.6 in a calculator. Root 7, you're looking at, what are your guideposts there? You're looking at 4 and 9, but you're pretty close to 9, so 2.6. The root of 0.69, you could think about 0.64 as your perfect square there. You're looking at 0.8. Cubed root of 24, again, these are just estimates, right? And I would want you comfortable giving me an explanation like those previous 2 slides for each one of these questions, okay? The cubed root of 24 is going to be really close to the cubed root of 27, which is 3, so 2 point something high, 2.8-ish, 2.9-ish, okay? Cubed root of 85, well, I know that the cube root, I know that 4 cubed is 64, and I know that 5 cubed is 125. So I'm 4 point something, okay, 4 point something. 4.4, it's 85 is slightly closer to the 64 than it is to the 125. The 4th root of 176, okay, same game, but my numbers are changing. For the 4th root, I am looking at 4 cubed is 64, and 4 to the 4 is my 256. So I know I have to be, oh, sorry, no, I'm looking at 4. So 3 to the 4 is 81, and 4 to the 4 is 256. That's what I meant to say there, sorry. 3 to the 4 is 81, 4 to the 4 is 256. So I know that I'm 3 point something, okay? Close to halfway there. It's about 100. So yeah, 3.6 is just slightly over the halfway mark. So then 5, or the 5th root of 26, I didn't give that to you on a table, but that's okay. You're just looking for guideposts. You know that 1 to the 5 is 1, and you know that 2 to the 5 is 32. So 26 is somewhere in between 1 and 32. It's closer to 32. So I know my answer is going to be 1 point something, right? Closer to 32, so that puts me into the higher range, maybe 1.8, 1.9, something like that. So I estimated 1.9, okay? All right, so your homework is listed here. Do take some time to practice, and if you do have any questions, you know where to find me. In the meantime, have a great day, and we'll talk to you on the next lesson. Take care, guys. Bye-bye.